Okay, we are finally at in-class exercise 3. Okay, so there's just one question. So for this question, you can see that hydrogen and NO, otherwise known as nitrogen oxide, they are reacting at 800 Kelvin, and you get two sets of experiments being carried out in an enclosed vessel. So they mentioned it's actually to determine the effect of the changing concentration of NO and H2 on the rates of the reaction. So the data you get was used to plot the graphs of initial rate against NO squared. I think you have to pay attention to this. You have to be very clear what you're plotting. So you're plotting initial rate against NO squared. Okay, so if you recall from what you have in the lecture notes, if you are plotting rates against concentration squared and you get a straight line that passes through the origin, this is very clearly second order kinetics. Okay, so therefore you can see that the initial rate is directly proportional to concentration squared. Okay, so in this case, if you are looking at rates is equals to K concentration of NO squared, and you're plotting rate against NO squared, and you get a straight line that passes through the origin. So in this case, it's very clear that the order of reaction with respect to NO is 2. And some of you might be wondering, hey, how about H2? Like H2 actually increases from 1.0 to 2.0 over here. You can easily look at the slope. So if I just pick any two numbers, okay, so let's pick maybe over here. Okay, so if we keep the concentration of NO squared a constant, this point is about 0.0065. Okay, and then this point is about 0.013. So you can see that as I double the concentration of H2 from 1 to 2, the initial rate doubles. Okay, so if this is not clear enough, maybe we can look at this point. Okay, if we keep the concentration of NO squared, or rather the value of NO squared constant at 0.0020, you'll notice that the initial rate in the production, okay, of the reaction goes from 0.013 to 0.026 when the concentration of H2 doubles from 1.0 to 2.0. Okay, so therefore you can easily tell that the order of reaction with respect to H2 is actually 1. Okay, so therefore the overall rate law is that NO and H2 to the power of 1. Then some of you again might be wondering, I mean that's a perfectly legitimate question. How come, although overall is third order, right? How come it is still a straight line that passes through the origin when you plot rate against concentration of NO squared? Well, if you notice from this whole system, let's say we look at just a random initial concentration of NO squared. So if you look at NO squared initial concentration will be 0.010, sorry, 0.0010. If we just take a square root of this number, okay, just take a square root. So the concentration of NO is about 0.032 moles per dm cube. Okay, what about H2? Concentration is 1 mole. So therefore, the concentration of H2 is way greater than the concentration of NO. Right? So in this case, it is actually a pseudo second order reaction with respect to NO. Okay, to be more exact. So any rate constant, if ever being calculated here, it will be K prime. Yep. Okay, so I think that should be the amount of details you need. Okay, so for part A, use the information from the graph above, deduce the order of reaction with respect to NO and H2. I think I've already answered that. I think so I mean, just to reiterate, first, you get a straight line that passes through the origin when you plot initial rate against concentration of NO squared. So therefore, you can conclude that the order of reaction with respect to NO is 2. And then as you double the concentration of H2 from 1.0 to 2.0, you realize that the gradient doubles. Okay, you can actually measure the gradient, the slope of this two graph. So the doubling in the gradient actually tells you that the order of reaction with respect to H2 is actually 1. Okay, and then this is the rate law that you should be writing, and then oh, they ask you to calculate the rate constant. Okay, no, I don't think it's a big issue. So since we have already written out the rate law, and let us just pick out a rate over here. So maybe we pick here. Okay, so in this case this is 0.052. Okay, so it's 0.052 equals to K. The concentration of NO squared here will be 0.004. Okay, so we just put 0.004 in, and then the concentrated hydrogen is actually 2. So we can easily obtain K to be about 6.5 per mole to the power minus 2, dm to the power 6 s minus 1. Okay, so this will be the calculation that we'll be doing for part B. Okay, yep. And of course, the important thing about this particular in-class exercise is really for us to take a look at the mechanism. Okay, so this particular mechanism is being proposed. Okay, so first of all, we have to look back first. The overall chemical reaction, you have two equivalent of NO reacts with two equivalent of H2 to give you one equivalent N2 and two equivalents of water. So the stoichiometric ratio is 2:2:1:2. So first of all, we must add everything up first to ensure that we get back the chemical equation. So let's try to do that. So we add everything up. N2O2 will be cancelled. N2O will be cancelled. And then we'll be left with 2NO on the left, 2H2 on the left. That makes a bit of sense. 2H2 on the right and 1N2 on the right. So, yep. So over the chemical, if you add the 3 elementary steps up, you will get the original chemical equation. So that's not a major issue. Okay, so right now we'll try to determine if the above mechanism is consistent with our answer in A. Yeah, so at first look, it doesn't seem so, because in your slow step, it involves one molecule of N2O2 colliding with one molecule of H2. So we'll just write out a rate expression first. So rate equals to K N2O2 to the power of 1 and H2 to the power of 1. Remember that your slow step should be reflected, okay, in your rate equation, okay, and the molecularity, meaning the stoichiometric coefficient, is reflected as the power. Okay, however, you might take note that N2O2, right, is actually an intermediate. So being an intermediate, it should not appear in the rate equation, okay, at all. So therefore we have to restructure our equation a little bit. Yeah, and we take note that the first step is actually a fast equilibrium. So if we let the equilibrium constant be Kc, so therefore that we'll take the product, which is N2O2 raised to the power of 1, because we have 1 here, and then over the reactant, the starting material, NO raised to the power of 2 because of the 2 here. Remember that for equilibrium constant, we raise the equilibrium concentration to the power, to the stoichiometric coefficient reflected in the equilibrium expression, or in the equilibrium reaction. Okay, we rearrange this, we'll be able to get N2O2 equals to Kc NO to the power of 2. And then we're going to substitute this whole thing into here. So once we substitute the whole thing into here, we're going to get rate equals to K and then Kc NO squared H to the power of 1. Okay, and of course this whole chunk can be represented by experimental rate constant, and this is obviously consistent with our rate law. Okay, so it's consistent with our rate law. Of course, when we write out our rate law, we'll just write out as K. We will not write out as K experimental. Okay, because that's a theoretical treatment. Okay, yep. So in that case, yes, the mechanism is consistent with the answer in A, because it reflects second order kinetics when I combine them up for NO, and then of course for H2. Okay, yeah. So if you are still unsure, maybe you want to go back to the notes and then do a little bit of revision regarding some of the content being covered. Okay, yeah. So because it's of vital importance for you to be able to deduce the rate law based on a simple 2 or 3 steps mechanism like what's given in part C, or the other way around. Given the rate law, maybe propose a simple 2 or 3 steps mechanism. Okay, the final part D is actually a recall question. Okay, it's a recall question. You were asked about using a labeled Maxwell-Boltzmann distribution curve. Explain how the rate of reaction changes when the reaction between H2 and NO is conducted at a high temperature. So I think the first thing you need to get your axis correct. So that's proportion of molecules. Okay, so this axis has to be correct. So you plot it against kinetic energy. Remember that you need to label your 0 points. Okay, or that's the origin. And then, well, I mean, you can use the same color. So maybe at a lower temperature, my curve will look like, oops, sorry. At a lower temperature, my curve will look like this. So that's T1. Okay, and then at high temperature, it will be broadened like this. Okay, and I will label the activation energy. So this is the activation energy, which is the minimum amount of energy you need before the reaction can kickstart. Okay, so if you want, you can do a bit of shading. You can shade over here. Okay, and then that's T1, right? So you can say you can just label this as the proportion of particles of molecules having Ke above Ea at T1. Okay, and then you can also indicate this as T2. You can shade T2. T2 is like this. And then here you can label accordingly proportion of particles having Ke above Ea at T2. Okay, when you sketch your graph, maybe one thing to take note of is that the area under the graph must be about the same. Okay, because we are looking at the same proportion of molecules or particles. Okay, so when you explain, you can say that, oh, as the temperature increases from T1 to T2, the proportion of particles having kinetic energy above the Ea increases. Okay, sometimes you might want to just showcase increases by this amount being shaded in green. If you want to, you can showcase that. And then therefore, the number of effective collision increases. Okay, you can say that as well, and therefore reaction rate increases. Okay, so I repeat, you can say that as the temperature increases from T1 to T2, the proportion of molecules with kinetic energy above the activation barrier increases by the amount reflected in the green shaded region. Okay, and because of that, you expect the frequency of effective collision to increase, and therefore this actually leads to an increase in the rate of reaction. And then a few things to take note of would be make sure that you have your origin over here, you have your axis properly labeled, you label your activation barrier as well, and make sure the graph you draw, the area under the graph is about the same, and the high temperature must be a graph that is broader, and the average kinetic energy, which means the peak, must be lower. Okay, because to keep the same area, when the curve broadens, the average Ke must lower, and it will lead to a lowering of the peak. Okay, yep, so that's the end of our debrief for